In this video, I want to try to address a couple of questions that came up as a result of the last video that I did discussing the real difference between mass and weight. And hopefully this video will clarify some of those questions for those of you who had questions. So what I'm going to do is just want to talk about the difference between mass and weight a little bit more, and maybe in even a little bit more depth. And I guess the best place to start out here is to start off with a definition. Well, as in the last video, one of the things you have to understand about mass and weight is that they are absolutely, totally different. Even though when we're here on the earth, we don't see the difference all that much. But think about it like this. By definition, mass is a measure of the amount of matter in an object, while weight is a measure of the pull of gravity on that matter. Think about it like this. You I'm sure have probably taken somewhere in the past, you might have taken a chemistry class, and in that chemistry class you learn that matter is made up of atoms. So there's an atom. Well, what part of the atom is missing? Well, the part of the atom that's missing right here is the nucleus. And the nucleus, you learned in chemistry, is that part of the atom that contains the protons and neutrons. And the nucleus is very tiny. Not only is it very tiny, but it's extremely dense, and it contains all of the mass of the atom. All of the matter that's in the atom is basically contained in that nucleus. So let me put a proton in here. As a matter of fact, I might even put a couple of protons in here. So there's a couple of protons in the nucleus of the atom, and joining them is going to be this neutron. So in this atom there are 3 particles in the nucleus. Each particle has mass, contains some mass. That is where the mass of the atom is located. If I were to add another particle in there, its mass would increase by 1. If I add 2 particles in there, its mass would increase by 2. If I take a particle out of the nucleus, its mass would decrease by 1 unit. So the mass of the atom is in the nucleus, and that's where mass comes from. When you think the word matter, you want to think of mass. And when you think of mass, you want to think of protons and neutrons. The matter in an atom are the protons and neutrons. The mass in an atom are the protons and neutrons. And what do you do with atoms? Well, with atoms you make objects, such as this iron ball or this wooden ball. Now both of these are the same size. They have the same dimensions, same diameter. And what you have to understand about each one, and you understand this very quickly, is if you hold the iron ball in your hand and then in the other hand hold the wooden ball, you find out very quickly that the iron ball weighs more. Well, it does weigh more. And why does it weigh more? Well, it weighs more because gravity is pulling down on both of these objects, giving each one its weight. But what is it that gravity is pulling on? Well, gravity is pulling on the matter, the mass that's in the nucleus of the atoms that make up the iron and make up the wood. So it is the mass that is now controlling the weight, but the weight is not going to exist without the force of gravity. Take away the force of gravity, the objects have no weight, but they still contain the same amount of matter, and therefore they still have the same mass. So what if we were to take the iron and the wood and our atom? What if we were to take these objects and take them to the moon? Let's take these objects to the moon. There's the moon. Well, if we take these objects to the moon has about 1/6 of the gravity of the Earth. And so you take these objects to the moon, they're still going to be under the influence of a gravitational attraction, gravity is still going to pull down on each one of these objects towards the moon. It's going to give them weight, but the weight is going to be less than it was on the Earth. It's going to be 1/6 as much. Why? Simply because the moon has less gravitational attraction for these objects than the Earth does, because the moon itself contains less matter, less mass than the Earth. And if you've ever studied anything about gravity, you know that the gravitational attraction between two bodies is proportional to the masses of the bodies. Both of the objects, or all three of the objects, have a lower weight on the moon than they do on the Earth, but the mass is the same. The mass is the same on the moon as it was on the Earth. Why? Because we didn't change the number of mass particles in the nucleus of the atoms. We didn't take any particles out of the nucleus of this atom. We didn't take any atoms and therefore particles out of the iron or the wood. And so all three of them have the same mass that they had on the Earth. They have the same quantity amount of matter as they did on the Earth. So that is a little bit, maybe, hopefully, more understandable concerning the difference between mass and weight. So one other question that came up from the other video was, why is it you can measure mass and weight on the Earth and they both appear the same? Well, let's take a look at how you actually measure mass and weight on the Earth. To be specific, when you measure weight on the Earth, you should measure weight with a scale. Not to say that you couldn't measure weight with a balance, but really, truthfully, when you measure weight on the Earth, you measure weight with a scale. And it works like this. You take a scale, and then on that scale, you place an object that you want to weigh, and then gravity is going to pull down on that object, and in doing so, it's going to either stretch a spring inside the scale or compress a spring inside the scale, or it's going to deform an electronic sensor inside the scale, and that is going to read as the weight of the object, the pull of gravity. You're measuring the pull of gravity. Now, as long as you're on the Earth, you can use that to measure weight, and you can also use it to measure mass. It will work for either one, as looking at a scale will tell you. The readout on a scale will read out, in many cases, in either newtons or in grams. One is a mass unit and one is a weight unit. Where this doesn't work is if you were to take this to the moon. Why? Because the moon has a different pull of gravity than the Earth does. And so that scale is not going to work the same on the moon as it is on the Earth. So what do you do? Well, what you would do probably is to use one of these. You'd use, on the moon or the Earth, you'd use a balance. And a balance is just that. You can use it to balance objects. So you take this balance, and on one side of the balance you place a known mass right there. And then on the other side of the balance you start adding mass until the beam levels off and balances. And at that point you know that you have the same quantity of matter on both sides of that balance. The same quantity of matter. In other words, when this beam is balanced, you know you have the same number of protons and neutrons on both sides of the balance. And that is mass. You use a balance to measure mass. And by the way, this balance will work whether it's on the Earth or on the moon, because it doesn't really depend on the quantity of gravity. It only depends on the gravity being there. There has to be some gravity to help you compare the masses on either side of that beam. So it makes no difference if you're on Earth's gravity or if you're on the Moon's gravity or Jupiter's gravity. This balance is going to read the same mass. So keep that in mind next time you pull out a scale to measure mass, that really a scale by definition measures weight, and a balance measures mass. So this works the same on the Earth, works the same on the Moon. But what do you do if you have no gravity to speak of at all, such as if you're in the International Space Station and you're orbiting the Earth? Well, you use one of these, and this is called an inertia balance or inertial balance, and it is exactly what the name implies. It operates with Newton's first law to measure mass. So let's go ahead and talk a couple of minutes about how this inertial balance works. And let me first of all describe how it's put together. The inertial balance, this one consists of two metal plates, one here and one out here on this end, and attached to the sides of the metal plates are these spring steel ribbons. They actually look like hacksaw blades. As a matter of fact, you can actually make one of these inertial balances with a couple of blocks of wood, one on each end, attached to a couple of hacksaw blades. If you stop and think about this, basically what an inertial balance is a horizontal pendulum. And this end, there's a C-clamp here that attaches this end of the inertial balance to this tabletop. This end out here is designed so that you can place weights in a tray, and it holds the weights securely so that they don't slide around. So here's how this works. If you take this inertial balance and start it swinging back and forth, in other words, give it a little pull and let it go and let it swing back and forth, it will oscillate back and forth with a frequency that is proportional to the mass that's on this tray. So if you don't put anything on it and just let it swing back and forth, it'll swing back and forth with a particular frequency, and you can calculate the period of oscillation. You can use a stopwatch if you wanted to and measure the period of oscillation. And then you would put a known mass on it, let it swing back and forth, and you'd again determine its period of oscillation. And then you'd put another known mass on it, let it swing back and forth, and determine its period of oscillation. And you would do that 4 or 5 times with known masses. And then if you put an unknown mass on it and let it swing back and forth, you can calculate with its period of motion or oscillation, you can calculate the mass of the object on the balance. And here is an example of a graph that you might have from one of these balances. And you can see here that on the x-axis we have the independent variable, which in this case is the mass that we've been changing. We have mass 1, mass 2, mass 3, mass 4, and plotted against that we have the period of oscillation on the y-axis. So at this mass, this was the period of oscillation. For the second mass, that was the period of oscillation, and so on. So we have 1, 2, 3, 4 different known masses and corresponding period of oscillations for each mass, and we plot that on a graph. And then we take an unknown mass, set it on the tray, let it oscillate back and forth, calculate the period of oscillation for the unknown mass, find that period of oscillation on the graph, and we can extrapolate the mass of the object. This balance, this inertial balance, does not depend on gravity. As a matter of fact, gravity acts in a downward direction, which is normal to the direction of oscillation of this inertial balance. So gravity has no effect on the reading of this balance, the mass measured by this balance. This balance will work anywhere where there is either gravity or no gravity. It will work on the space station orbiting the Earth in free fall. It'll work on the moon. It would work anywhere in the universe because it doesn't depend on gravity. It depends measuring mass against the inertia of the object that's placed on it. So that gives you a little idea of the difference again between mass and weight. The key thing to remember is that mass is literally a measure of the quantity of matter, that means protons and neutrons, that an object contains. And that is absolutely independent of where you are on the moon, on the Earth, on Jupiter, in outer space. The amount of matter remains the same, the number of protons remains the same, and therefore the mass of the object remains the same.